Hello APC Mechanics students, today we will solve the past paper of RQ Set 2 2019 exercise 1. Then let's start. Blocks of mass m and 2m are connected by light string and placed on a frictionless inclined plane. The inclined plane is frictionless. That makes an angle theta with the horizontal as shown in figure 1 above. Another light string connecting the block of mass m to a hanging sphere of mass capital M passes over a pulley of negligible mass and negligible friction. Then here in this case the pulley is ideal, which means the tension here, which is T2, will be transmitted equally along the other end of the rope. The entire system is initially at rest and in equilibrium. This is very important, so we can at any moment use the balance forces. Before doing so, we need to utilize, as usual, the FBD of different systems. Then part A, on the dots below that represent the block of mass m, the sphere of mass m, draw and label the forces, not components, that act on each of the objects shown. Each force must be represented by distinct arrows starting on and pointing away from the dot. Then they're giving us instructions for the FBD. Now we need to do two FBDs for small m, which is given by this one. What are the forces acting on small m? We have the tension up, we have the tension down, we have the pull of gravity, and we have the normal force, normal push, no friction because friction is negligible. Then let me represent these forces. So we have the pull of gravity down, and I will say, instead of writing Fg, because here also I will be representing the pull of gravity, I'm gonna say Mg. And we have the tension up the ramp, we have the tension down the ramp, and we have the normal push, perpendicular to the ramp. Then let me say this is capital N, that would be T2, and that would be T1. Now here in this case it's not necessary that T1 should be equal to T2, although they are balanced, but remember that actually T1 should be less than T2 because there will be part of this component helping the tension in order to balance T2. Now remember that in the FBD it's not mandatory to place the angles that the vectors make with the horizontal or with the x-axis and the y-axis, but it's better for us in order later for projection. Then this is the angle theta. No, sorry. Let me say this is the y-axis. Then that would be the angle theta. Now for the capital M, what are the forces acting on capital M? We have the tension T2 up the string y. T2 here is equal to T2 because the tension is transmitted equally, and we have the pull of gravity down. So we have the pull of gravity being down, and here we need to make sure that T2 should be balanced with the pull of gravity. So that would be capital Mg, and that would be T2. They are perfectly equal because the sphere is at equilibrium or at rest. Now this is it for this page. Now let's move to part B. In part B, they're telling you derive expressions for the magnitude of each of the following. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figures in part A. So remember that if we need to do components, for example, components won't be represented here because they are FBD. If you need to do an additional FBD, we cannot draw here because this is our solution for part A. Now idea 1, the force T2 we need to derive. So basically we refer to part B. We need to derive the force T2 exerted on the block of mass m by the string. So we need to determine the tension T2. Express your answers in terms of m theta and the physical constants as appropriate. Then whenever we derive the final solution, we should double check the sentence. Then if we refer back to the FBD, we need to determine the tension T2. Now basically tension T2 appears in two FBDs, in this one and in this one. Okay, but if you refer back to the question, they're telling you we need to express our answer in terms of m, and small m refers to this FBD. So I'm gonna utilize this FBD in order to determine the expression of T2. if we utilize this FVD in order to determine the expression of T2, we would express it in terms of capital M. For this reason, I will refer to this one. So now what are the forces? So first of all, which direction I will consider? T2 lies along the x-axis. Suppose this is the x-axis. Then I'm gonna say that T2 will be balanced by T1 plus mg. If this is cosine theta, then that would be sine theta. So let me write here that we have the T2 equals T1 plus mg sine theta, and the reason is given by balance forces. And now we're searching for the expression of T2. Already this part has been expressed in terms of m and theta and physical constants. Now what about T1? We need to get rid of T1, and T1 can be determined by referring to the FPD of this one, which we didn't represent. So let me do quickly the FPD of this block. Now let me say that this is the ramp. So this is the block given by mass 2m. We have the pull of gravity being down. That would be 2mg. And we have the normal push, which is perpendicular to the ramp. And we have the tension T1 up the ramp. And if this is the y-axis, then that would be the angle theta. So also we can say that T1 is being balanced by 2mg sine theta. So now we need to say that T1 is equal to 2mg sine theta. And this is also because they are what? Balance forces. Now this expression would be replaced here. So we have the T2 equals the double of mg sine theta plus mg sine theta, which leaves us with an expression of T2 given by 3mg sine theta. And indeed, everything is being expressed in terms of m, theta, and physical constants as appropriate. Don't expect that they will tell you to express your answer in terms of sine, because sine is a function and not a variable or a constant. Now in section 2 we refer again to part B, and we need to derive the expression of capital M. And in order to derive the expression of capital M, in this case we need to utilize the FPD, which is here. Then we're gonna say that T2 equals to mg. They are balance forces. Then T2 would be equal to mg, and they are balance forces because the system is at equilibrium. Then each part of the system is at rest, and we need to find the expression of m. So we need to replace T2. Already T2 has been determined in idea I to be 3mg sine theta, and that would be 3mg sine theta equals to capital M multiplied by g with g cancel. Then the expression of m in terms of m, theta, and physical constants is given by 3m sine theta. Now, as a part of the free response paper, we expect that there might be some questions that are conceptual regarding argumentations or variations. We need to pay attention whether justification is required or no. If it's not required, then we'll just choose the correct or the most convenient choice. Idea C. Now suppose that the capital M is large enough to descend and that the sphere reaches the floor before the blocks reach the pulley. So what's happening here is that suppose the mass of M is large enough, then the system will move down. So the blocks will move up the ramp and the sphere will move down. Now the sphere will hit the ground before these two reach the pulley. Answer the following for the moment immediately after the sphere reaches the floor. So all of these questions will be answered based on the fact that the moment that the sphere hits the ground and these blocks, they didn't reach the pulley. Now they're asking you for the tension. Does the tension T1 increase, decrease to a non-zero value, decreases to 0, or stay? So let me repeat. Does the tension T1 increase? increase, decrease to a non-zero value, or decrease to 0, or stay the same. So we have 4 options. Now the moment this sphere reaches the ground, if you imagine what's happening here, this is being launched up with a certain velocity. So the moment this hits the ground, this string will lose tension because this will be projected up, and this string will become loose, which means that the tension T1 along the string would be 0. So the correct answer would be decrease to 0. And if you notice carefully, they didn't ask for any justification, so that would give you the full mark. Is the velocity of the block of mass m up the ramp, down the ramp, or 0? Now initially, when this is going down and it hits the ground, it's being projected up by a certain velocity. So its velocity of the block m, it's up the ramp. Then the correct answer would be C. Sorry, would be up the ramp. Now idea 3 is the acceleration of the block of mass m up the ramp, down the ramp, or 0. Now the moment this sphere hits the ground, also this string will lose tension. So what are the forces momentarily after the sphere hits the ground? It's being acted only by the pull of gravity, which is down. Remember that this string will also lose tension, so the acceleration, so the pull of gravity is down, then the net forces are down. You can ignore the normal push because it will be balanced by the vertical component or the y component of the pull of gravity. So basically it will be pulled by the acceleration down. Therefore the acceleration would be after the sphere hits the ground, it would be down. So down the ramp. Now part D, consider the initial setup in figure 1. Now suppose the surface of the incline is rough and the coefficient of static friction between the blocks and the inclined plane is mu s. Now we have switched friction on. Derive an expression. We need to derive for the minimum possible value of m that will keep the blocks from moving down the incline. So we need to derive an expression for the value of m that will keep the blocks from moving down the incline. So basically we need to find the value of m which is enough in order to avoid the blocks from moving down. And whenever we say minimum and you consider reading this sentence again, you will understand that here we're talking at the verge of motion. So we can use the fact that the friction, which is the static friction in this case, is given by mu s multiplied by Fn. Remember that this cannot be used whatsoever unless we are talking about the verge of motion. It happens here because we're talking about the minimum possible value of m. Then we're referring to the verge of motion. Express your answer in terms of m, mu s, theta, and fundamental constants as appropriate. Then in order to do so, we're still not moving, we're still at rest. So we need to utilize the FPD of a certain system, but which system specifically? Because they have mentioned the capital M, it means that we're gonna utilize this FPD. But remember that our answer should be expressed in terms of mu s, which means that also we will use the FPD related to the other blocks. So first, let me refer to these blocks and apply the balance forces, or let me do the FPD. The thing is that here we can either consider 2m, or we can consider m, or we can consider them combined to be a mass of 3m. So I will consider them to be one object of mass 3m. Then let me represent its FPD here. So let me suppose that this is the ramp, and this is the block combined of mass 3m. We have the pull of gravity down, given by 3mg. Now that would be the y-axis, along which the normal push is acting up. So already I have used here capital N. So let me say this is n prime, not the derivative, is just n prime, or let me say this is n1. Alright, we have the tension. So basically now these two are combined and being acted by the tension T2 up. Now remember that we need to add friction. What is the tendency of motion of the system? We're determining the minimum possible value of m. We'll keep the blocks from moving down, so the tendency of motion is down, then friction would be up the ramp. So that would be FF. Now we're ready to say that these forces are balance forces. Now that would be angle theta. Then the component along the x-axis would be 3 mg sine theta. Then I would say that 3 mg sine theta would be equal to the tension T2 plus the friction force. Now remember that we're interested in determining the value of m. So now T2, we know that, and we have determined, and we've said that T2 is equal to mg because these are balance forces. Then T2 here can be simply replaced by mg. Plus FF. We're interested in determining the value of m. It's okay with this expression. It's being expressed in terms of m theta and fundamental constants. We're interested in determining m, but now we need to find FF. FF, because we're at the verge of motion, is given by mu s Fn. Now what about the normal push? In this case, the normal push is given by N1, so let me use the same notation, N1. So N1 would be equal to 3 mg cosine theta, and the thing is that this is balance forces. Now this expression here would be replaced here, and this would be replaced here. So let me say that we have, that would be equal to mu s multiplied by 3 mg cosine theta. Then in this case, let me proceed here. Then we have 3 mg sine theta equals to capital M multiplied by g plus mu s 3 mg cosine theta. Now luckily g with the g cancel. We are interested in finding capital M. Capital M, if we move this to the other side, that would be 3m sine theta minus 3m mu s cosine theta. In order to make our expression look more perfect, we can factor out 3m, but remember that this is not a mandatory step. Once you reach this expression, that would be fine. Sine theta minus mu s multiplied by cosine theta. So indeed our expression have been expressed in terms of m, theta, mu s, and as usual don't expect that they will talk about sine or cosine. Now in part E they're telling us the string connecting the block M and the sphere of mass M then breaks and the blocks begin to move from rest down the incline. The lower block starts a distance d from the bottom of the incline as shown in figure 1. The coefficient of kinetic friction, friction, directly changes from being static to kinetic between the blocks and the inclined plane now is mu k. Derive an expression for the speed of the blocks when the lower block reaches the bottom of the incline. Express your answer in terms of md mu k theta. So we need to determine the expression of the velocity at the bottom of the ramp, knowing that these two blocks will remain. So let me refer again. We need to determine the velocity of whom exactly. So derive an expression for the speed of the blocks combined. So we assume that the tension T1, this string will remain inextensible, so it will hold tension. So they move as a single system of mass 3m under the influence of gravity and opposed by the kinetic friction. So let's recall that, remember, for a free falling body in air the acceleration is g. On a frictionless ramp it's given by g sine theta. On a rough ramp is given by g sine theta minus mu k cosine theta, but remember that we cannot use this formula before we derive it. So first we're gonna derive it using Newton's second law, and after we do that we can apply kinematics equation in order to determine the speed at the bottom of the ramp. And to do so we need again to utilize an FBD, so let me do it quick. This is the FBD, that would be 3m combined. We have the y-axis like that, along which the normal push is always acting. So let me say this is N2, or it's the same as N1, no big difference, because N1 is the normal push due to m and 3m. So we don't have tension. We don't have tension T2 because now the string breaks. Okay, we have the pull of gravity being down. So that would be 3mg for the masses combined, that would be the angle theta. And now let me say apply in Newton's second law, and that would be F naught is ma. What are the different forces acting on the 3m combined? That would be the pull of gravity. Pull of gravity plus the normal push N1 equals the masses combined 3ma. Now we're gonna project along the ramp, which is basically the x-axis. The pull of gravity is in the positive direction, which is I consider to be down. That would be 3mg sine theta. Sorry, here I forgot to add friction. So we have a friction because they are moving down. We have friction to be up, and this friction is kinetic friction, so plus ff equals ma, and that would be 0 minus ff, which is, so this is 3ma. Now 3mg sine theta minus mu k n1 equals 3ma. Now remember n1 has been determined to be 3mg sine cosine theta. So change this again. Now as you can see, this expression would be mass independent, and indeed the acceleration is given by g as a factor, sine theta minus mu k cosine theta, as we claimed previously. Now we know that because all of these are constants, then the acceleration is constant, then the type of motion is uniform varied motion. And we need now to find the velocity. We can use either the velocity related to time or velocity related to distance. Since we need to express our answer in terms of distance, I will use the following equation of motion given by v square x is v square x0 plus 2a delta x. Let me repeat again and say why we are allowed to use such type of equations, because we know that these now are all constants, then the type of motion is uniform varied motion. Referring to the exercise, we can see that the block starts from rest, then that would be 0. So vx square would be 2 multiplied by the value of the acceleration, which is given by g sine theta minus mu k cosine theta multiplied by delta x, which the distance the block down will travel, which is d. Then now vx, which is the speed at the bottom of the ramp, would be given by radical of 2, so here we have a bracket, 2gd multiplied by sine theta minus mu k cosine theta. And let's do the final check. Indeed our speed is being expressed in terms of d, g, which is the physical or fundamental constants, mu k and theta, and we haven't used the mass. That's fine. Then that's it for me in this video, guys. See you soon in a new one.